Introduction. I'm Ling Zhang from Shanghai Jiao Tong University. So today I'm going to present our recent work on verified compilation. Particularly, it's about verified compilation of multi-threaded programs which may share stack data between different threads. This is a joint work with these people. First, I will introduce the background of verified compositional compilation, or VCC for short. The compiler correctness is usually defined as refinement between semantics. Here, this notation denotes that the semantics of M1 is refined by that of M2. So for, So for example, the state-of-the-art verified compiler for C, CompCert, it compiles the source program foo.c into the target program foo.s. Here, this refinement ensures that all the possible behaviors of the target program is included by that of the source program. So any desired property on the source program can be preserved to the target program. For open programs, the modules are separately compiled into target programs, and as VCC, we need to ensure that these refinements can be composed to get the refinement of complete programs. So we need to formalize and verify the interaction between these open modules. For sequential programs, these interactions are mainly in the form of function calls and returns. For multi-threaded programs, similarly, we prove the compilation in the form of refinement. But the point here is different threads may interfere with each other via context switches, which is much more harder to be verified than function calls and returns. So there has been a great amount of work on achieving different kinds of VCC. Here we only focus on the extensions of CompCert, which is usually used as the foundation of verified compilation. So compositional CompCert first achieves the verified compilation of open programs. Then thread-safe CompCertOC and CompCert achieves verified compilation of multi-threaded programs. However, the shared stack is not supported in these works, which means one thread cannot access the stack data allocated by another thread. This has been an open program since then. And recently, we have more works on the VCC for sequential programs, which introduce new techniques for the reasoning of memory. So this work is going to use the framework comes from nominal CompCert and CompCertO to address this open problem. So that's why it's named CompCertOC, C for concurrent. So now let's see why shared stack is a problem in multi-threaded programs. Here we have a running example of parent and the child threads. The parent thread will allocate its two local variables I and TID. It then uses pthread create to create a child thread and pass the address of I to it. Then the child thread may update the value of the shared variable I, and the parent thread will join it and print the value of I. I think this is a very common practice in multi-threaded programming, where the two threads share a shared variable I, but it's not formally supported by any existing compositional compiler. Here the main challenge is how to verify the simultaneous stack sharing and protection, where the variable I is shared between these two threads, while another variable TID should be protected from the child thread. Otherwise, the pthread join may found the wrong target, right? So one sentence for our contribution is we, for the first time, achieved verified compositional compilation for a multi-threaded program with shared stacks. Our work is based on rely guarantee reasoning, which is a very common technique in compositional verification. Based on it, we introduced two key ideas: the threaded open simulation for final-grained rely guarantee conditions, and the threaded Kripke memory relation for memory protection. We have also successfully integrated our framework with CompCertO, which gives us CompCertOC includes 18 of 20 parsers in CompCert v3.13. Using this compiler, we are able to achieve verified compilation of heterogeneous programs. So in the remaining of this talk, I will be mainly focused on the two ideas and briefly introduce our applications. Notice that the following discussion is based on cooperative multithreading, where context switches are caused by thread primitives. The connection to preemptive multithreading is left for future work. So I will start with the first key idea. I will first talk about the background for sequential programs and the challenge in multithreading, and finally our solution. So the background refinement relation between sequential programs is usually defined as open simulation. As you can see, the program states of source and target programs are related at each point during the execution. And when they call external calls, they make a rely condition on the environment. And on the other hand, this simulation provides a guarantee condition from the initialization to the finalization. Note that rely guarantee conditions in such open simulation are only defined for complete function calls, which means we know absolutely nothing from the initialization to external calls or from the returns to the finalization. Symmetric rely guarantee conditions can enable the composition of open simulations. As you can see in the example on the right, if the rely condition of the caller can be satisfied by the guarantee provided by callee, then these two refinements can be composed. Let's see a concrete example of compilation, or here is the optimization at the source level. This is two sequential programs. This was sequential program caller, where J is caller's private variable. You can see it's only used in the printf and it's never leaked. So the compiler may remove it out of the memory and propagate its value to the printf command as a constant. We shall agree this simple optimization is correct, while this correctness actually relies on the assumption that the J in source variable is never changed by the external callee, right? So from now on, we will focus on the execution and the interaction between source programs. For simplicity, again, this rely condition should be satisfied by the guarantee condition provided by the callee. Therefore, they can be composed. Now let's see why this doesn't work for multi-threading. This is our running example for parent and child again. The parent thread will create and the switches to the child thread. And similarly, we have a rely condition that TID is not changed by the child. One possibility of the execution here is that the child thread ends its execution, it returns and switches back to the parent thread. In such situation, it's pretty the same as the sequential case. The guarantee condition of the child function can guarantee that it does not change the private variable TID. So it seems like context switches could be treated similarly as function calls. But we have another possibility, that is the child thread switches back before its return. In such situations, the open simulation of child provides no guarantee to enable the composition, because remember that rely guarantee conditions in open simulation is only defined for complete function calls. So the problem here is we need a guarantee condition for partial execution. Now let's extend the open simulation for sequential case to get our threaded open simulation for multi-threaded programs. The first step is to introduce context switches. We use the same rely on external calls and the context switches because they look similar from the perspective of an open module. The second step is to introduce internal guarantee of internal executions to satisfy the rely of context switches. The guarantee condition from initialization to finalization is preserved and renamed into external guarantee. So this is a complete diagram of threaded open simulation, which we use it as the refinement between open multi-threaded programs. The rely condition can be satisfied by different guarantees in different situations. So now we still have a remaining problem, is how to define these rely guarantee conditions for all programs and for all possible executions in the multi-threading. To answer this, the main challenge is actually the general definition of memory protection. So here comes our second key idea. It's called threaded Kripke memory relation. It's the same pattern from background to challenge and solution. Again, this is our example of the sequential programs. Here we present the picture of memory states. Again, the caller has a rely condition that the variable J should be unchanged during this unknown external call, and is satisfied by the guarantee condition provided by the callee. So the rely guarantee condition here for the memory protection is that the private variable j should be unchanged during this external call. This memory relation is usually can be described using memory accessibility. It's a general definition from Kripke relation. To establish such accessibility from M1 to M2, which basically says that M2 is a valid successor of M1 after an external call, we need to do 2 steps. The first step is to mark the private regions in M1. In our example, it's very simple. It's just the variable j. But the formal general definition of private regions is actually related to the compilation. And I do not have time to discuss it here. You can find it in our paper. The second step is to ensure that these regions are unchanged in M2. Quite simple. So also, the guarantee condition provided by the callee is defined using the same memory accessibility. So in summary, for sequential programs, the rely guarantee conditions are defined using the same accessibility, so they are symmetric and can enable the composition. Now let's see why this doesn't work for multi-threading. This is again the parent and child thread example. The difference is here, we assume that the child thread also allocates its own private variable k. And the execution starts after pthread create, which means child thread is created at in the very beginning, the same as its private variable k is in the initial memory. Then similarly, the parent switches to the child thread, and the child thread may modify k and use it to increase the child variable I. Then it switches back to the parent. In this example, the direct guarantee, you can see is only TID should be protected during this context switch, while k could be changed by the internal execution of child. This is distribution. So if we try to use memory accessibility to describe these conditions, we'll see it fails because it cannot distinguish between TID and k. They are both private variables in source programs. The only difference is they are allocated by different threads. So the problem here is the coarse-grained protection of private memory for all threads is not sufficient. So what we need is a finer-grained memory protection for each thread. So here comes our solution. It's called threaded Kripke memory relation. The key point here is we define 2 different memory accessibilities. The first line is external accessibility, which requires that the private memory of the current thread is unchanged. Well, the internal accessibility requires that the opposite, the private memory of the other thread should be unchanged from M1 to M2. Using these accessibilities, we can define the memory evolution in the rely guarantee conditions like this. As you can see, the rely condition and the external guarantee are defined using the same external accessibility, while the internal guarantee for partial executions are defined by internal accessibility. Now let's revisit our example. Here, the rely condition of the parent from M1 to M2 is defined using external accessibility, which assumes that TID is unchanged as its local private variable, while k does not need to be protected because it is external variable allocated by the child thread. On the right, the internal guarantee of the child thread also ensures that TID is unchanged, but as its external variable. So, and its local variable k can be changed by its internal executions. So as a brief summary, these 2 different memory accessibilities make sure that rely on external calls can be satisfied by external guarantee of the callee, which is pretty the same as the sequential case, and rely on context switches can be satisfied by internal guarantee of all other threads. Now, based on the 2 new mechanisms for rely guarantee conditions and memory protection, we are able to support verified compositional compilation of multi-threaded programs with shared stacks. Now I will briefly introduce our applications to demonstrate the capability of our approach. The first application is the CompCertOC, which is a verified compositional compiler for C using POSIX primitives and with shared stacks. To integrate our framework with CompCertOC, we need to first implement the key ideas and update the proofs of individual passes in the CompCert. Then we need to compose the multiple compilation passes to get the compiler correctness from source to target. We also need to compose the separate modules and threads. This integration actually took us 10 months and 20.3K lines of code in total. So there are quite a lot of technical challenges in this integration, but I don't have time to discuss them here. If you are interested, please read our paper. Another application is the verified compilation of a heterogeneous multi-threaded program. This is actually the running example in our paper, which includes a client and server both written in C. The client will create a child thread for the server, and the server will further call an external call, which is actually implemented in the handwritten assembly encrypt.s to do some encryption. To verify this example, we shall first introduce the specification of encrypt.s and verify it using threaded open simulation, which is exactly the same notion of the compiler correctness. Therefore, these three refinements can be composed to get the backward simulation between closed multi-threaded programs. So for conclusion, to the best of our knowledge, we are the first time to achieve verified compositional compilation of multi-threaded programs with shared stacks. I have introduced our two key ideas, threaded open simulation for like-guarantee conditions and threaded encryption memorialization for the memory protection. We have also developed CompCertOC and used it to achieve verified compilation of complete programs. For future works, we may try to connect our work with preemptive semantics or the verification of multi-threaded program. Okay, that's all. Thanks for your attention, and I'm ready to take questions.
We have time for a couple of questions. Okay, let us kick us off. So thank you very much for the accessible talk, even though I'm not an expert in the field. I liked your examples very much.
Thank you.
So one question that popped to my mind is, so you had this example where you had I, and then on the stack, the next variable was pi, okay?
Yeah.
And then you passed the pointer to I to the other thread.
Yeah.
What happens if the other thread actually changes the pointer and just says pointer +1 and then starts to modify this? Then this should no longer be private, but so how do you deal with that?
It's actually, sorry, I'll get to it. It's, yeah, I think this is. So as you just said, it can be some bad things when the callee here changes the variable of j by using some bad pointer arithmetic. So that's why we need to verify it can provide the guarantee. So as I just said, the compiler correctness depends. It has an assumption that the callee does not do some bad stuff like you said. So of course the compiler correctness, again, the compiler correctness depends on the counterpart does not do some bad stuff. That's it. I think it's mainly. So if possibly you get some assembly code that actually does these bad things, and in that time you are not able to verify it to be composed with a compiled program. Yeah, that's it.
I see. Thank you. Are there questions from the audience? For people who are more qualified than me to ask questions. No. All right. Cool. Thank you very much. I think that's very exciting work. Thank you.